What the Study Says.
Welcome back to What the Study Says. I'm Dr. Kai.
And I'm Dr. May.
So today we're jumping into the 2025 Nobel Prize in Physics. It went to John Clark, Michel Devoret, and John Martinis.
Right. And their work tackled a really fundamental, almost, weird question. Can something big enough to actually hold, like an electrical circuit, still play by the bizarre rules of quantum mechanics?
It sounds like something out of science fiction, doesn't it? The idea that quantum effects, superposition, tunneling, aren't just for single atoms.
Exactly. So our mission today is to unpack how they managed to prove this back in the mid-'80s. They showed that macroscopic quantum mechanics, MQM, is actually real. It was a huge leap.
Okay, let's set the stage. What was the system they were actually looking at?
Well, the core of it was a special kind of superconducting circuit. And the key component, a Josephson tunnel junction.
Right, that's the sandwich structure, isn't it? Two superconductors with a really thin insulating layer in between.
Precisely. And the genius part was realizing they could describe the behavior of, billions of charged particles moving collectively in that circuit.
As if it were just one single quantum thing.
You got it. One coherent quantum entity. And they came up with a great way to visualize it.
Ah, the washboard analogy. I remember reading about this.
Yeah, it's perfect. They modeled the system like a tiny particle rolling on a surface shaped like a tilted washboard.
Okay, so if the whole circuit acts like one particle, what is that particle representing physically? It's not like a specific electron, right?
No. The particle in the analogy represents the phase difference of the superconducting wave function across that junction. It's the macroscopic variable.
The collective property of the whole system.
That's the one. If the system is truly quantum, then that phase difference, that macroscopic thing, is what has to be obeying quantum rules, like being quantized.
Got it. So on this tilted watchboard, what are the important states for the particle?
There are basically two states we care about. First, the zero voltage state. The particle is stuck, temporarily at least, in one of the dips of the washboard. It's a metastable state.
Stable, but not perfectly stable.
Exactly. And the second state is the non-zero voltage state. This happens when the particle escapes that dip and starts rolling freely down the tilted washboard.
And when it rolls, that corresponds to a voltage suddenly appearing across the actual circuit.
Bingo. You can measure that voltage, so the escape event is detectable.
So the big question, the whole point of the research, was proving how it escapes.
Precisely. Does it escape because the whole circuit just gets warm enough, thermal jiggling, that the particle just shakes its way over the barrier? That's the classical way.
Or does it escape using purely quantum effects?
Right. Specifically, quantum tunneling through the barrier, even if it doesn't have enough energy to go over it, or by jumping between discrete quantized energy levels within the dip.
Okay, so classical heat versus quantum magic. How do you even begin to prove the quantum part is real?
This is where the real careful science comes in. Before you can claim anything quantum, you have to nail down every single classical effect perfectly. You need to rule out heat completely.
You need to know your enemy, basically.
Exactly. So that precursor work, mostly around 1984, was all about calibration. Classical calibration.
Because they wanted the final quantum result to stand on its own, right? No fudging the numbers, no adjustable parameters.
That was the goal, the smoking gun proof. So they needed to measure everything about their specific junction while it was running its critical current, its capacitance, its resistance, how quickly oscillations died down, which is called the damping factor.
All a classical characteristic.
All of them. They started in what you could call the warm regime, relatively speaking, of course, about 4.2 Kelvin liquid helium temperature.
Still incredibly cold for us,
Yeah.
but warm enough for classical physics to dominate the escape.
Right. At that temperature, the particle escapes purely because of thermal fluctuations, just random heat energy kicking it over the barrier.
And measuring that escape rate gave them real numbers.
Yes, there's a well-known equation for thermal escape rate. By fitting their data to that equation, they could directly measure things like the critical current of their junction and confirm the temperature of the thermal bath. It gave them their baseline.
But then they did something really clever for calibration, didn't they? This resonant activation.
Yes, resonant activation. This was their precision tool for mapping the classical system. They applied a very faint microwave signal to the circuit.
Microwaves. How did that help?
Well, think about the particle sitting in its little washboard dip. It can jiggle back and forth naturally at a certain frequency, the plasma frequency.
Okay.
Now, if you shine microwaves on it and the microwave frequency happens to match that natural plasma frequency,
It resonates, like pushing a swing at just the right moment.
exactly like that, the particle absorbs energy very efficiently from the microwaves, jiggles much more violently, and escapes the well much faster. Its lifetime in the zero voltage state plummets.
So by finding the exact microwave frequency that caused the fastest escape, they can measure the system's natural frequency.
Precisely. They could measure the plasma frequency, omega p, and also, very importantly, the damping factor, Q, basically how much friction the particle experienced on the washboard.
How sticky it was.
Yeah, how quickly the jiggling died down. They measured Q values around 13 in some early experiments, and later got them up to about 30 in the junctions used for the quantum tests.
So all this meticulous classical work, measuring escape rates, using resonant activation, it gave them an exact experimentally determined picture of their washboard potential.
Absolutely. They knew the barrier height, the oscillation frequency, the damping, everything, determined purely classically. No guesswork.
Okay, the classical stage is set. Now for the main event, proving the quantum behavior.
Time to go cold. Really cold. They had to cool the circuits down below about 25 millikelvin. That's thousandths of a degree above absolute zero.
Why so cold?
To starve the system of thermal energy. At those temperatures, the thermal energy, kBT, becomes much, much smaller than the quantum energy scale, which is set by the plasma frequency times Planck's constant h bar omega p.
So basically, there just isn't enough heat energy anymore for the particle to climb over the barrier classically.
Correct. If the particle escapes now, it almost has to be doing something quantum. And the first big proof they found was macroscopic quantum tunneling, MQT.
Tunneling, the particle going straight through the wall.
That's the idea. They measured the escape rate as they cooled the system down, and what they saw was amazing. Below a certain temperature, around 25 millikelvin,
Yes.
the escape rate just stopped changing. It became completely independent of the actual bath temperature. Didn't matter if it was 20 millik or 10 millik, the particle escaped at the same rate.
And that flatness, that temperature independence, is the classic sign of tunneling.
It's the smoking gun for tunneling. It means the escape isn't driven by thermal energy anymore. The macroscopic particle, the phase difference, was quantum tunneling through the potential barrier.
Wow. And could they predict what that tunneling rate should be?
Yes, and this is the most crucial part. Using those parameters they had painstakingly measured back in the classical regime using resonant activation.
The barrier height, the frequency, the damping?
All of it. They could calculate, using quantum mechanics, what the escape rate due to tunneling should be at absolute zero temperature.
Did it match?
It matched beautifully. They characterized the observed temperature-independent escape rate by an escape temperature. The measured value was 37.4 plus or minus 4 millikelvin.
Okay.
The theoretical prediction, based only on their earlier classical measurements with zero free parameters, was 36.0 plus or minus 1.4 millikelvin.
That's incredible agreement within the error bars.
It was stunning confirmation. It proved the escape mechanism had shifted from classical thermal activation to quantum tunneling, exactly as predicted by quantum theory applied to their measured classical parameters.
So MQT confirmed. But they didn't stop there, did they? They also showed energy quantization.
Right. Another fundamental quantum idea. If that particle is trapped in the washboard dip and it's truly quantum, it shouldn't be able to have just any amount of energy.
Like electrons in an atom can only be in specific energy shells.
Exactly the same principle. It should only exist at discrete, allowed energy levels E0, E1, E2, and so on.
How on earth do you measure those tiny energy steps in a macroscopic circuit?
Microwave spectroscopy again, but used in a different way. This time, they kept the temperature very low in the quantum regime and shone microwaves on the junction while slowly changing the bias current flowing through it.
Why change the current?
Changing the bias current subtly changes the tilt of the washboard potential. And changing the tilt changes the shape of the potential well the particle is trapped in.
And changing the shape of the well changes the spacing between those allowed quantum energy levels.
Precisely. So they could effectively tune the energy level spacing. They swept the bias current, effectively sweeping the energy difference between levels, say between the ground state E0 and the first excited state E1.
Until that energy difference exactly matched the energy of the incoming microwave photons.
Yes, and when that happened, resonance. The microwave photon gets absorbed, kicking the macroscopic particle from the lower energy level to the higher one, say E0 to E1 or E1 to E2.
And promoting it to a higher energy level makes it more likely to escape.
Much more likely. So whenever the microwave frequency matched a specific energy level transition, they saw a sharp peak in the escape rate.
Discrete peaks, not the broad hump they saw in classical resonant activation.
Exactly. Sharp, distinct peaks corresponding to transitions between specific quantum energy levels. And the positions of these peaks, the bias currents where they occurred, matched the predictions from quantum mechanics perfectly.
They could even see multiple peaks, right? Like E0 to E1 and then maybe E1 to E2.
Yes, they observed several distinct transitions. It was clear evidence that the energy of this macroscopic variable was quantized. And importantly, these quantum resonance peaks were at different positions than where the classical plasma resonance prediction would be.
So completely different physics. And they saw the crossover too.
They did. At the very lowest temperatures, like 18 millikelvin, they saw these sharp quantum peaks. As they gradually warmed the system up, the peaks got broader, started to merge.
And eventually smoothed out into that single asymmetric hump characteristic of the classical resonant activation they'd studied earlier.
Right. It beautifully showed the transition from purely quantum behavior at low temperatures to the familiar classical behavior at higher temperatures, all within the same device. It nailed both NQT and energy quantization.
And you mentioned something about coherence time. How long did this quantum state last?
That was also a key finding. They estimated that this macroscopic quantum state, this collective phase difference, remained coherent, maintained its quantum nature for times up to about 40 nanoseconds.
Which might not sound long, but for a macroscopic system behaving quantumly.
It was actually quite significant, especially back then. And it's that coherence, that ability to maintain a quantum state for a measurable time, that directly connects this foundational work to why they got the Nobel Prize decades later.
Okay, connect those dots for us. How does proving MQT and energy levels in a junction in 1985 lead to today's quantum tech?
Well, this work was the fundamental proof of concept. It showed that you could build superconducting circuits where a macroscopic variable behaved quantum mechanically, and importantly, that you could potentially control and manipulate that quantum state, at least for short times.
Control being the key word.
Absolutely. The ability to put the system into a specific quantum energy state, like the ground state, keep it there coherently for a bit, and then potentially excite it to another state, like the first excited state, with microwaves.
That sounds awfully like the basic operations needed for a quantum bit, a qubit.
It's exactly the foundation. This research directly paved the way for superconducting qubits, particularly the transmon qubit design, which is a workhorse in many of today's leading quantum computers. They essentially refined these early Josephson junction circuits.
So the Nobel Committee cited the impact on the next generation of quantum technology. They really meant it laid the groundwork for things like quantum computers.
Without a doubt. Quantum computers, but also potentially things like ultra-sensitive quantum sensors and perhaps even secure quantum communication protocols. It all builds on being able to engineer and control macroscopic quantum states.
It's amazing how it bridges the gap. We already rely on quantum mechanics for things like transistors in our computers and phones, right?
Yeah.
But that's sort of letting quantum mechanics do its thing.
Right. We leverage the results of quantum mechanics in transistors. But this work by Clark, Deveritz, and Martinis was about actively engineering and controlling a macroscopic quantum system. That's the critical difference, the leap towards true quantum technology.
Looking back at the whole story, what really stands out is the incredible scientific rigor. That detailed classical calibration wasn't just a side project.
Oh, it was absolutely essential. The resonant activation work, nailing down those classical parameters like omega p and q without any ambiguity.
That's what made the later quantum results so undeniable. They could predict the quantum behavior with no adjustable parameters, no wiggle room.
It's textbook scientific method, really. Eliminate every classical explanation first, then make a quantitative prediction based on those classical measurements, and then see if the quantum experiment matches the prediction. And it did.
It really highlights the painstaking work behind major discoveries. So as we wrap up, what's the big takeaway thought here?
Well, think about this. They achieved these results in circuits that were, by today's standards, only just barely cold enough, only marginally in the deep quantum regime. The coherence times were tens of nanoseconds.
Impressive then, but maybe not by today's qubit standards.
Right, but if that system, one you could literally hold, showed clear quantum tunneling and energy levels, even briefly, it really makes you wonder, where's the boundary between the quantum and classical worlds?
Is it fuzzier than we think?
Mm-hmm.
Could much larger systems potentially exhibit quantum behavior if we could isolate them well enough?
Exactly. If a circuit with billions of particles acts quantumly at 18 millikelvin, what are the ultimate limits? It suggests the weirdness of quantum mechanics might extend much further into our everyday world than we usually assume. It certainly opens up fascinating questions.
A truly mind-bending thought to end on. We hope this deep dive into the physics underpinning the 2025 Nobel has given you a clearer picture of this incredible science.
Thanks for joining us on What the Study Says. If you found this interesting, please do subscribe and maybe share this exploration with others. We'll see you next time.